Okay, this is lesson 3.1 from Mrs. Cucci's College Now Pre-Calculus class. Corresponds to day, I'm not sure what day it corresponds to. 3.1, make sure you have this open. Okay, so what we're going to be talking about in this unit is something a little bit different than what we've done. And it is going to be on polynomial functions and rational functions. So we're going to get into some pretty interesting stuff, okay? So by the end of this lesson, you're going to be able to determine the behavior of a graph of a polynomial function using what's called the leading term test. You're going to be able to factor a polynomial function and find their zeros and their multiplicities. You're going to be able to use the calculator to graph a polynomial function and find its real number zeros, its relative maximum, minimum values, and its domain and range. And you're going to be able to solve applied problems using polynomial models. You're going to be able to fit linear, quadratic, power, cubic, and quadratic polynomial functions to data. A lot of this stuff you guys already know how to do, but we're going to put it in conjunction with other things that make it new material. Okay, so a basic polynomial function looks like this, okay? Where you've got your coefficients, a sub n minus 1, a sub 1, a sub 0, and so on. And those are all real numbers. And the exponents are whole numbers. So just going to give you an example would be like 2x to the fourth minus 3x squared plus 2x minus 3. Okay, that's a polynomial. You've got your exponents descending by 1 each time, right? And then your coefficients, which are some number, okay? And then your variable, okay? So that's a basic polynomial function. All right, so the first non-zero coefficient, a sub n, is what we call the leading coefficient. So that's the one that sits out front, and it is attached to the variable that has the highest exponent. The term a sub n times x to the nth is called your leading term. And the degree of the polynomial function is n, okay? So leading coefficient is on the leading term, which includes the degree of the polynomial, which is your largest exponent. Okay, so we're going to state the degree, the leading term, and the leading coefficient. So the degree, that's what we're going to start with. The degree is the number of the exponent, okay, the exponent to the variable. Since the variable here isn't shown, it's going to be x to the 0, okay? So your degree is 0. Your leading term is 3, and your leading coefficient is 3, because it's the only thing we have there, okay? B is a little bit different. We're going to go in the order of degree, leading term, leading coefficient. So the degree, the exponent to your variable, which is 1. Your leading term, which is your first term here, 2/3 x. And your leading coefficient, which is whatever sits in front of the variable, is 2/3. Next one, degree is 2. Leading term is 4x squared. And your leading coefficient is 4. So notice all that information comes from the same term in that function. Okay. Degree, 3, largest exponent. Term, x cubed. And leading coefficient, because nothing's written, 1. Degree on the last one is 4. Leading term, negative x to the 4th. And leading coefficient, negative 1. So that should have been pretty simple. Again, you've been doing this since 9th grade, so this isn't new. Okay, so there are some functions that you need to be able to know just by looking at them, and this is one of them. Okay, so I've got my quadratic function. The function is x squared minus 2x minus 3. Okay, and we need to be able to pull a whole bunch of information from this quadratic. So we're going to use our tools to do that. First, we need to figure out what we actually want. So on the next page, I have a list. I want the zeros, the x-intercepts, the y-intercepts, the minimum or the maximum, the domain, and the range. So let's start with zeros. We know that zeros are where the function crosses through the x-axis. Another word for zeros is roots or solutions, right? So we're looking at these two values here. Now this one is done really pretty for us, right? It goes right through these values and they're easy to find. We've got the values of -1 and 3. So those are our zeros, okay? We also wanted the x-intercepts. Well, those x-intercepts are the same, but x-intercepts, as you guys learned, have to be written as points. So this is the point -1, 0, and this is the point 3, 0. So those are our x-intercepts. Our y-intercept is where it crosses through the y-axis, and that's the point 0, -3. Okay. Minimum, our minimum point, right? Minimum point looks to be right here. That minimum point is 1, -4. Maximum, well, since this is a quadratic and it has a +1 for a leading coefficient, we're not going to have a maximum. We're only going to have a minimum. My domain. My domain is all the x values being used. And since we know that this expands out forever, we're going to continue to use x values as we go. That domain is going to be from -infinity to infinity. And my range, what y values are being used, well, we're starting here, they're at my minimum, and we're going up. So my range values are from -4 to infinity. So I know I just put a whole bunch of information on here, right? But it wasn't information that you guys didn't already know how to find. So what we're going to do, we're just going to put that information in here. Okay. So again, my zeros were -1 and 3. My intercepts were -1, 0 and 3, 0. My y-intercept was 0, -3. My minimum was -4. Sorry, 1, -4. My maximum, I didn't have one. My domain was all real numbers from -infinity to infinity. And my range was -4 to infinity. I'll be recording. Okay, so we're going to try another one of these, but this time we're not going to do a quadratic. We're going to do a cubic function. Okay, so a cubic function is a function that has a degree of 3. So we're going to find this information as well. Now, a lot of this we can, again, just look at and determine by looking at the graph. Okay, so let's start with my zeros. Again, my zeros are where it crosses through the x-axis. So we've got one here, here, and here. And my scale on this is kind of funky. I think I want to change my scale. Let's change this to 1. Not sure why it's at 0.2. This is just going to make it easier. Hello. There we go. That's much easier to see. Okay, so my zeros occur where it crosses the x-axis. So my zeros are at x equals 3, -1, and -3. Okay. This is -4, not -3. So those are my zeros. We also want my x-intercepts. So we know that those are just written as points from your roots. So we get 3, 0, -1, 0, and -4, 0. Okay, we have my y-intercept, which doesn't look like it gives us a nice pretty value. So we are going to have to use the technology to figure that out. Okay, so you're going to use menu, geometry, points and lines, and you're going to do point on. Okay, just click on that graph, hit enter, and then grab that point and drag it until you get where it says y-intercept. It looks like I moved it a bit. And we get the point 0, -12. Okay, so let's put that information down that we have so far. Actually, let's go on to relative max-min. Okay, so again, we've got that relative max, relative min. And what we can do is we can actually use that point on again, and it's going to say minimum for us at that minimum value. Okay, and we can pull it to the other side, and it'll say maximum for us when we hit it, and there's our maximum value. Okay. Domain is all the x values that are being used, so we are going from -infinity to +infinity. We're using all x values. And our range, same thing. This is shooting down to -infinity, whereas this is going up to +infinity. So your range is going to be from -infinity to +infinity as well. So let's get that information down on the next page. Okay, my zeros are -4, -1, and 3. My x-intercepts are -4, 0, -1, 0, and 3, 0. My y-intercept was the point 0, -12. My minimum was 1.4, -20.7 approximately. And my maximum was -2.7, 12.6 approximately. Domain, again, was all real numbers from -infinity to +infinity, as was my range. Okay, let's go to the next page. All right, so all of the following graphs are known as polynomial functions. They're all going to look a little bit different, but you do have to know just by looking at them that they are polynomial functions. Okay, so I've got 4 on this graph here. My first one is a basic quadratic. Okay, basic quadratic, which you guys are used to seeing. That is a polynomial function. The next one is a constant. Okay, y equals -3. That is a polynomial. Even though it doesn't have any variables that you can see in it, it's still a polynomial function. Next one is my cubic function. I've got 2x cubed plus x squared plus x minus 1. That's polynomial. And then the next one is a quadratic, so it's x to the 4th. And you need to be able to look at these and know what type of function they are visually. Whenever you have a cubic, they're all going to have this same general shape where it's kind of like that funky stretched out S. And then the x to the 4th is kind of going to have that bump in it. So it's going to look like a quadratic, but it's going to have that bump. So if you keep in mind here, this is an odd index. This is an even, or I'm sorry, an odd power. This is an even power. This is an even power. Notice how they extend. On either side, the end behavior for a quadratic is going the same direction. The end behavior for my quadratic, my 4th power, is also going the same direction. My odd power, one is going up and one is going down. And this is going to become important to us shortly. Okay? Okay, so again, all of the ones, the last 4 were known as polynomial. The next 4 are non-polynomial functions. So that's our absolute value, our radical, our ones with our exponents, and our rational. Okay, so these 4 are not polynomial functions. They're not written as polynomials. So this is what is a little bit different. Okay, so again, you need to be able to look at them and know what type of function it is visually. Okay, so you probably saw that the graph of a polynomial function is continuous, meaning that if we were to graph it, we wouldn't have to pick up our pencil. there's no holes, there's no breaks, and it's also smooth and there's no sharp corners. Okay, so that was these function here. They were all continuous. I could very easily draw those in as a nice smooth curve. These ones, not so much. We've got missing pieces. We have to jump from one function to the other as we're graphing it. We've got sharp edges. So these, there is a difference visually between them. Okay, so let's look at a few examples of discontinuous functions. Okay, so an example of a discontinuous function. If I had, let's say, this function here, okay? This function is discontinuous because if I were to go and trace it, I would get stuck here and have to hop up here and then hop down here. I have to pick up my pencil, which makes this a discontinuous function, okay? Another example of a discontinuous function would be something like this. Again, if I went to graph this, I'd go here and I'd have to pick up my pencil to hop over that point. Okay, so these are examples of discontinuous functions. Okay, so next thing we're going to talk about is something called the leading term test. The behavior of a graph of a polynomial function as x becomes really big or very large as it goes to infinity or very small as it goes to negative infinity is referred to as what we call end behavior of the graph. And we're going to do a lot of work with end behavior. The leading term of the polynomial function determines the end behavior. So we have a couple of rules that you kind of have to memorize. Okay? Not kind of, you do have to memorize it. So if I've got my leading term a sub n times x to the n, my leading term of my polynomial, then we've got these behaviors that can be described, that should be can, not cab, sorry, in the following ways. Okay, so if my exponent, right, so let's say I have x squared and x cubed, okay? If my exponent is even, x squared, x to the fourth, x to the sixth, then what's going to happen is if that exponent is greater than 0, meaning 2, 4, 6, it's going to shoot up to positive infinity on either side, from on the left and right. So the end behavior to the left, to negative infinity, is the same as the end behavior to the right, or positive infinity. Okay? If it's an even power, but it's less than 0, meaning x to the negative 2, x to the negative 4, x to the negative 6, same thing's going to happen. As I approach negative infinity, I'm going to shoot down. As I approach positive infinity, I'm still going to shoot down. Okay, so the end behavior is the same from the left and the right when we have even exponents. And when we have odd, it's a little bit different. Okay, when we have an odd index, x to the third, x to the fifth, x to the seventh, x to the ninth, as I approach positive infinity, so going to the right, my graph is going to shoot up to infinity. As I approach negative infinity to the left, it's going to go down to negative infinity. Okay? So odd power, positive odd power, to the right up, to the left down. Negative odd power, x to the timeout. Sorry, guys. I was thinking negative x squared, negative x to the fourth, negative x to the sixth. Sorry about that, guys. Negative x cubed, negative x to the fifth, negative x to the seventh, negative x to the ninth. All of these are going to have that same trait, okay? But as I go to negative infinity, it's going to shoot up. As I go to positive infinity, it's going to shoot down. So you have to have these rules memorized, okay? So again, even power, it's going to have the same end behavior as I approach negative infinity to positive infinity. Okay. Negative even, it's going to approach negative infinity as I go to negative infinity, positive negative infinity as I go to positive infinity. Okay. So as x gets greater, we're still going down. As x gets smaller, we're still going down. Odd powers. As x approaches infinity, we are going up to infinity. As x approaches negative infinity, we're going down to negative infinity. If I make that a negative, negative, when I go towards negative infinity, I'm going up to positive. Positive infinity, I'm going down to negative. Okay, so you're going to have those memorized. I would suggest making it foldable. All right, guys, we're going to pause here. We're going to finish up this video tomorrow, so please make sure you come prepared with any questions. Thanks, guys.